From the movies Netflix just knows you're going to love, to the way your bank can instantly spot a weird transaction on your card, we're surrounded by technology that feels weirdly smart. It kind of feels like magic, right? But behind the curtain, it's all about machines that have learned how to do this amazing stuff.
So, let's get into it. How does a hunk of code go from being a blank slate to making these incredibly smart predictions? Well, it's definitely not magic. It's actually a set of really distinct, fascinating processes. And today, we're going to break down the 3 main ways that machines learn.
So here's the game plan. We're going to start with supervised learning. Think of it like learning with a teacher. Then we'll dive into unsupervised learning, which is more like being a detective with no clothes. And after that, we'll tackle reinforcement learning, basically learning from trial and error. And at the end, we'll tie it all together.
All right, first up, supervised learning. And the core idea here is actually pretty simple. You basically give the machine a huge data set that's already filled with the right answers. You label everything. The machine then just studies all these examples, kind of like a student cramming for a test with a full answer key.
A perfect way to think about this is trying to decide on a movie. You could just ask your best friend, right? They know what you like, they've seen how you've reacted to a bunch of other movies, and that's your labeled data. That's the basic idea. But, in the real world, just relying on one friend's opinion, it's not always the best bet. So, what do?
Well, you ask a whole group of your friends, of course. And that's exactly where an algorithm like random forest comes in. In the world of machine learning, each one of your friends is what we call a decision tree. And by combining the opinions of hundreds or even thousands of these trees, the machine's final guess gets way, way more accurate.
And how it works is surprisingly straightforward. The algorithm builds a whole forest of these decision trees, and each one gets to see a random little piece of the data. Each tree then gets a vote. Yep, you'll love this movie, or nah, skip it. The final decision? It's just a simple majority vote. It's basically the wisdom of the crowd, but for machines.
And of course, this isn't just for picking your next movie night. Banks use this exact logic to approve or deny loan applications by looking at past data. In medicine, it can predict if a patient is at high risk for a disease. And huge companies like Amazon use it to figure out if a customer looks like they might be about to leave. This thing is a real powerhouse out in the world.
Okay, let's shift gears to our second type of learning. What happens if you don't have an answer key? Well, that's unsupervised learning. With this one, we give the machine a whole bunch of data with absolutely no labels, and we just ask it one simple thing. Find the interesting patterns in here.
And this slide really nails the key difference. See? Supervised learning needs the question and the right answer, but unsupervised learning, it only gets the questions. It's like the difference between studying with a practice test that has all the answers in the back versus being handed a giant box of old photos and being told to sort them into family groups.
Now, the most common thing you do with unsupervised learning is something called clustering. Imagine someone just dumps a huge bag of mixed fruit on your table. Your job is to sort it out. Even if you have no idea what an apple or a banana is, you just naturally start grouping them, right? By color, by shape, by size. That's exactly what clustering is, finding the natural groups that exist in the data.
So how does a machine actually do this? Let's take a look using a really popular algorithm called k-means. First, you just have your cloud of unlabeled data points. Then, the algorithm just randomly plops down 2 starting points. We call these centroids, and you can see them here as the red and blue x's.
Okay, for step 2, the algorithm looks at every single data point and asks a simple question. Which x are you closer to, the red one or the blue one? And then it just colors each dot based on the answer. And just like that, we have our first very rough guess at the clusters.
But this is where the magic happens. The algorithm now finds the dead center of all the newly colored red dots and moves the red x there. Then it does the exact same thing for all the blue dots. See that? The centroids are already starting to shift towards the real center of those groups.
And from here, you just repeat. Assign the points to the closest center, then move the center. Assign, move, assign, move. After just a few runs, the centroids stop moving. And boom, the algorithm has found the 2 distinct groups that were hiding in the data the whole time. And it did it all without a single label to help.
Now, k-means is super popular because, well, it's fast and it's pretty easy to understand what's going on. But it's not perfect. The biggest catch is that you have to tell it how many clusters to look for ahead of time. That's the K. And if you guess the wrong number, your results are going to be pretty much useless. It also gets confused by weird outliers that can drag the center of the cluster away from where it should be.
All right, let's get to our third and final type, reinforcement learning. And this one is a whole different animal. It's completely different from the other two. This is all about learning by doing, through endless trial and error.
Honestly, the best analogy for this is just picturing a baby learning how to walk. I mean, there's no instruction manual, right? The baby just tries to take a step, that's an action. If they fall over, whoops, that's negative feedback. But if they manage to wobble their way over to a toy, that's a positive reward. And over thousands and thousands of these little experiments, they slowly figure out the best way to walk.
So in reinforcement learning, you have three key parts. The first is the agent. That's the learner, the one making the decisions. So in our little story, the baby is the agent. The agent then lives inside of an environment. That's literally everything it can interact with. For the baby, the environment is the living room, the floor, the coffee table it can bump into, you name it.
And finally, and this is the most important part, the agent's actions are guided by a reward. This is the feedback it gets from the environment. It could be something good, like a piece of candy for success, or something bad, like a painful bump from a fall. The agent's entire goal is to take actions that get it the most reward over time.
And this leads to this really fascinating problem called the exploration-exploitation trade-off. Think about it. Should the agent exploit what it already knows works to get a pretty good guaranteed reward? Or should it explore and try something totally new and risky that might lead to an even bigger reward? Or might lead to nothing at all? Finding that perfect balance is the secret to mastering pretty much any complex problem.
Okay, let's zoom out for a second and bring this all home. So, to recap, we have supervised learning. That's our student with the answer key, learning from perfect examples. We have unsupervised learning. That's our explorer, charting new territory and finding hidden patterns in the wild. And finally, reinforcement learning. That's our player, trying to master a game through trial, error, and chasing those sweet, sweet rewards.
Each one of these methods is incredibly powerful, but for a long time, they've learned from these neat, carefully prepared datasets that we humans feed them. And that leads to the really big question everyone is asking right now. What happens when these models, these new foundation models, stop learning from our small datasets and start learning from basically all the text and images on the entire internet? What new things could they learn then?